Yep.
So hi everybody, welcome. For those of you joining on YouTube, it's April 28th. This is Precalculus. So today we're going to finish up polynomials, and then we have some modeling questions that we're going to look at, sort of to give us some examples of where we might see polynomials pop up in some application questions. So last time we spent time thinking about this factor theorem. So Nick and I were just talking about this, where you can relate factors of polynomials to the zero. So we have this nice theorem that says a number c is a zero if and only if x minus that number is a factor. And so what that tells us is when we see stuff like this, we know that if I have a factor of my polynomial x minus 15, then 15 has to be a zero. And similarly, if you're given the zeros, what we can do is we can say, hey, if these are my zeros, I know what some of the factors of my polynomial have to be. Okay, so I was talking to Nick, and he said, well, what we should see by the factor theorem is that x minus 1 and x minus 2 and x plus 3 should all be factors of our polynomial. Okay, so I agree with that sentiment, right? So we'll do x minus 1, x minus 2, x plus 3. Okay, so if we have these three factors, we can see that our zeros are the ones that we want, right? -3, 1, and 2. And if we go back to our notes, right, 1, 2, -3. And so I threw out this question. I said, well, certainly here is a polynomial, the one that we just constructed on Desmos, right here, that has the information we want. But how many can you make? Can you make more than this? Can you just make this one? Or what are some sort of different ways that we could modify this, where I want to make sure that I have these zeros, but we might have, other information in there. Okay, so how many different polynomials can you make that have these zeros? Right? Can you come up with at least one more?
So if we just multiply that entire thing by 6 or any number really.
Okay, so I could put in a 6 over here like this.
Yeah.
Right, so then that, right, it looks like my zeros remain unchanged, right? And then we still have a polynomial. We could put any number here, right? So we could put like 0.5 if we wanted to, right? And then our zeros still remain unchanged. Okay, so one way that we could modify it is we could have our coefficient out here change. Okay, is there something else that we could do that?
Could we take one of these terms to an exponent?
Yeah, so we could square this term, right? So if I square this, let's check my zeros again. Where does it cross? We have a -3, a 1, and a 2. And it seems like here, this is still a polynomial, and we still have the same zeros, but it's somehow different, right? So I could do the same thing, right? I could cube this, or I could make this to the 10th power or something, right? Right. We're still only going to have these zeros. Now, this is a really messed up polynomial on Desmos, but right, we can see that we're not changing the zeros. We're changing some other stuff about this polynomial. Okay, so let's just stick with 1, right? So just to make our lives easier, we'll go back to our original one. We've seen that we can make a bunch of different things, but so let's observe what happens when I change, say, the exponent on this term, x minus 1. Okay, so here's this factor, x minus 1, goes along with this 0 right here. So let's just sort of keep in mind what's happening right here. And then I'm going to go ahead and square it, and we're going to see how it changed. Right, so if I put a 2 there, what was different than if I just put a 1, right? So I guess we can we can do this in Desmos. We can actually graph both of them side by side, right? So when I had, if I'm just zooming in on one here, we'll notice that, hey, well, when I had just a 1 as an exponent there, this is the behavior that I see. When I have 2 as an exponent, we see this behavior right here, yeah? So do you see the differences there, Nick?
Yeah.
So can you describe that in your own words, what you see in there?
I guess the line's going up from the 1, and then it's kind of like at the top of, for when it's squared, it's kind of at the top of an upside down parabola.
Okay, so it's like you have this parabola here where it comes up and that's the peak and then it comes back down.
Yeah.
Okay, and then what about in this case?
It's kind of like it's on the side of the parabola.
Okay, so let's see if we can. Let's have another one here. We'll make it. Let's make it green, and let's make this a 3. Okay, so three different polynomials here. All I'm doing is changing the behavior on this exponent. So if we have an exponent of 1, this is sort of the behavior that we see at 1. We have an exponent of 2, we get sort of this behavior at 1. And we have an exponent of 3, we get this behavior at 1.
It's like more loopy the higher the exponent. Like there's more curves.
Okay, so let's try another one. Let's make it an orange and let's make it a 4. What do you think, what's your prediction that's going to happen here if I make this a 4?
I'm gonna guess there's gonna be like more curves. It's gonna change direction more often.
Okay. So here's sort of building up, right? So if I just look at the even ones, are these similar in some way?
Yeah.
So let's make one to the 6th power, okay? And then we can make it purple or something. So what's sort of similar about all of these?
They all kind of have the same basic shape, but as the exponent gets higher, they kind of flatten out.
Yeah, they flatten out right around here and come back down. Yeah, so they're all hitting at that one point. So do they? To me, when I'm looking at this, it seems like they all stay on the same side, right? So it's like they come up to this point and then they bounce off and then they come back down. Right. So if I think about just locally here at 1, they never cross. Like there's nothing up here.
Yeah.
But if I switch it off, right? So I just look at the odd ones. It seems like what we're doing is we're crossing, right? So we actually cross the x-axis here. Let's throw in a 5th power just for good measure, right? So it seems like if I look at the odd numbers, right, they actually cross the x-axis here and come back down. And then when I look at the even numbers like this, they kind of bounce off the x-axis there, and then they come back down. So when we're thinking about zeros, what we call this number right here, we call this a multiplicity, right? So we have a 0 at 1 with multiplicity 4, with multiplicity 5, with multiplicity 6. And so these multiplicities actually give you some information about the function, right? So you can look at this and say, hey, I actually know what's going to be happening close to that 0. And so if you look at certain graphs, you can pick off that kind of information, right? So you might not know exactly what the multiplicity is, but there's a very distinct visual difference between a multiplicity, an even multiplicity, and an odd multiplicity. So either depends if it's going to cross the axis at that particular point. Right, so without even factoring or anything, right? So we haven't really done a whole lot of algebraic manipulation, but we're sort of looking for patterns in our structure here, and we're able to pick out behaviors based on those patterns. Right, so this question right here, there's really a lot in there, right? So we've only explored part A, but it seems like, hey, if I know the zeros, that gives me some information, but as we saw here, if I really wanted to narrow down exactly one polynomial, I would have to know more than that, right? I would have to know maybe what the leading coefficient is, right? Because that could change, and then I might need to know the multiplicities of my polynomial, and I might need to know maybe the degree of my polynomial. So I do need more information than just the zeros, right? So that's not enough to give me precisely one polynomial. Okay. And so for these others, right, we can do something very similar, right? So if we wanted just any polynomial, we could do all of our factors would be x minus, and then whatever these numbers are.
Mm-hmm.
Okay. But what about this, right? So were you able to come up with an equation for this, right? So if I look at this, were you able to model this exactly?
Let's see.
Like when you look at this, what's something that you see right away? Like what
zeros?
Yeah, zeros, right? So what are your zeros are here, right? And what are they?
-2, 1, and 4.
Okay, so right away I already know, like, if I go over to Desmos, that -2, 1, and 4 should be there, right? So I should have zeros at these places. So what we can do is we can over here. All right, so let's get rid of this. So we have -2, 1, and 4. Right, so those should be our zeros. Okay, so here's my graph, and if I come back over here and I compare it, there's some distinct differences, right? So this one, the zeros are in the right places. It looks like we have the right shape, but what I want is, it seems like this one is way up here at like 10, and then this one is up here maybe at like 3 or 2-ish. So it seems like this one is too high over here, right? What I want to do is kind of squash it down. So is there some other piece of information that we could pick off this graph that might help us? Like, what do you think the degree of this polynomial is?
I'm not sure.
So I come over here, what's the degree of this polynomial that we've drawn in here?
Third?
Yeah, this is a third degree polynomial, right? So if I look at this, to me, it looks like this is the general shape of a third degree polynomial, right? You get this classic sort of shape right here, right? So to me, this is a third degree polynomial, and what I need to do now is I need to, figure out how to get these, this peak to sort of come down. It seems like it's too high over here. This one's too low. I want to squash the graph like this.
I think if you multiply it by 0.25, that gets you about the right graph.
Okay, so did you guess at that?
Yes. I tried multiplying it by different numbers.
Yeah, so you put like a 2 here. Ooh, that went the wrong way. Maybe I want a half, right? And then you just kind of tried stuff like this. So that's one approach that you could do. And so sometimes if you're doing that, right? So if you put in 0.25, then it seems to look about right. Okay, so that was through guessing and checking. Let's see if we could do that without guessing and checking. Okay, so what we found so far is, right, we said our polynomial is x plus 2 times x minus 1 times x minus 4. And if we look at our graph, one additional piece of information, we could have 1 point, okay? So this point on our graph is 0, 2, right? So what I'm going to do is, it tells me if I plug in 0, then I should get an output. I should get an output of 2. Okay. So let's jump over here to our Blackboard and see how we might do this. Right. So what we want is there's going to be some number that we're going to multiply out front here to our polynomial, and we want to figure out what that is, right? So I don't want to have to guess and check at it. Right. So my polynomial is going to be something like this. And what I do know is that I want the point 0, 2 to be on the graph. Okay, so what this is telling me is that f of 0 should be equal to 2. Right, so whenever I have an input of 0, I should have an output of 2. So what you get is 2 is equal to a times 0 plus 2 times 0 minus 1 times 0 minus 4. Right, and so if I multiply all this out, I get a, and this is 2 times negative 1 times negative 4. And so all that becomes 8. Right, and so what you get is a is equal to 1/4. So do you remember doing something similar like this when we had quadratic equations? Right, so we had the 2 zeros and we picked any other point, we could figure out what the equation of the quadratic was.
Yeah.
But this is the same process, except we have more factors now, right? So
Okay.
right, so if we, in this case, what we're doing is we looked at that graph and we said, hey, it's a cubic. It looked like all of our multiplicities were 1, right? So remember, we didn't know exactly what our multiplicities were. Those weren't given to us. We sort of inferred that. But then once we set up that structure, we were able to take one additional point, and then that gave us what our leading coefficient is, right? In this particular case, with the information that we picked out. Okay, so coming over here, right, 0.25, that's the same as 1/4, right? So if we wanted to write it out the way we had it, right? So this equation, 1/4, x plus 2, x minus 1, x minus 4, gives us this right here.
Okay.
And then so down here, this question 8, right, when I want to factor these things using Desmos, did you have a sort of a general procedure for going through that? What were you doing to factor these things?
I just I typed them into Desmos and then found the zeros.
Okay, so let's see if I can just copy paste this. So you had 5x cubed, right? Minus 3x squared minus 5x plus 3. So this is part C, or yeah, part C down here, right? This is our h of x. 5x cubed minus 3x squared minus 5x plus 3. Okay, this is h of x. All right, so you found the zeros. So you got negative 1, 0.6, and 1. Okay, so what's next? What's the next step?
So, and then I typed those out into like an equation in the factor. So I did x minus 1, x plus 1, x minus 0.6.
Right, so x plus 1 goes along with this negative 1, 0. X minus 0.6 goes along with this one, and then x minus 1 goes along with that one. Right? So it looks like these are the right zeros, but the black line and the green line look different to me.
Yeah. So then we need to find a number that to multiply by.
Yeah, and so do you think, so we could do what we did before, right? So we could pick a point, like maybe this one right here. We could do the algebra out, but since I already know the equation, right? So do you think that we could find like a faster way to get that leading coefficient? right? What would that number that has to go out here be?
So could we just set it up and do the factored form times a and set that equal to the equation?
We could, yeah. So just like we did before, we could do the exact same thing and we would get our answer. But my question for you is, in this particular case, you don't have to do that, right? So since you already have the equation, right? When I multiply all of these out, what's the leading term of this polynomial going to be, right? When I multiply all this together, what is going to be my leading term?
5.
Yeah, but in this one it is, right? 5x cubed. But when I multiply this one out, am I going to get 5x cubed?
No.
What are you going to get?
1.
1x cubed, right? So I don't want that to be 1x cubed. I really want that to be 5x cubed. So what do you think my coefficient out here should be?
5.
Yeah, right. So if we already have the equation, if I already know what my leading term is, and I already know what my leading coefficient is, we don't necessarily have to go through that same process, right? So in this case, we're working a little bit smarter because we have more information, right? So in this case, we have more information than we did in the previous case. Okay, so with this graph, we didn't have the equation, and this one down here we do, right? So we are given the equation, and so we know what that leading coefficient has to be 5. Right? So if you can pick off the zeros, if you want to factor a polynomial, right? You can look at this, you can take off the zeros, and you're going to have to infer what some of the multiplicities are in some cases, depending on the behavior of the graph at those points. And then your leading coefficient will always be the same as we go through. Right, so when we want to factor something like this is a lot nicer, right? So this process, using Desmos, using technology, I think this is a nice example of thinking with the computer rather than letting the computer think for us, right? So we have a nice example of this here. All right, so have you, in your previous math history, did you sort of ever go through factoring polynomials like this?
Not that I remember. I may have.
So I mean so it is a laborious pursuit for sure. There's lots of, if you were going to try and factor this, it's really something. And so, but with Desmos, right, using just a little bit of understanding this factor theorem, sort of some understanding about multiplicities of zeros and then leading coefficients, and we can actually do quite a bit, right? This process isn't too bad, right? So there's not too much work that we have to do, just some thinking and picking out the right details.
Mm-hmm.
Okay. So I think I'll ask you, do you have access to a piece of paper and some scissors?
Yes.
Okay.
I'll be right back.
All right, so while Nick is off getting some supplies from home, so if you're watching along at home on YouTube, this would be a good time we're going to walk through a modeling problem here, and then we're going to have a piece of paper, right? So you can see on the screen here this modeling activity. These are what we're going to need. Tape. You could use tape if you wanted to. You don't have to if you want to sort of put your box together. But we're going to take a piece of paper that looks like this, right? So 8.5 by 11, just a regular sheet of paper. And what we're going to do is we're going to make a box out of it. Okay, so when we make a box, we're going to try to make the box that has the biggest possible volume. And so this is what we call an optimization problem. Right, so you have some sort of constraints, right? You have to make a box out of a piece of paper using this diagram, and we're going to try to figure out how we can make the largest possible volume, and then we could also think about things like, what's the smallest possible volume. So optimization problems are something that is very important in calculus. So in my calculus class right now, we're looking at a lot of the similar problems, except we kind of kick it up a notch where we don't have all the parameters. We are going to have to use calculus to help us solve these problems. Things like maximizing profit or minimizing waste or minimizing travel time or minimizing packaging materials. Right? These are all important questions that come up in a business setting, and many people around the world, right? Anytime you're trying to do something, you want to do it in the most efficient way possible. And calculus is a great tool that often helps us determine, where those optimal values are. So Nick, I don't know if you're back, but
Yep.
let me know when you get back in here.
Yep, I'm back.
All right. So you heard my little speech there about optimization?
Yeah, I heard the end of it.
All right. So when we go on to take calculus, right? This is sort of one of the big applications. How do you optimize, right? So most efficient ways to do things, least amount of waste, most amount of profit, least amount of time, things like that, right? You might be hearing, all over the world, people want to, say reduce a carbon footprint or something, right? You hear these terms in the news. You want to minimize them, right? What are some of the things that you could do, right? So for that particular example, right, if you wanted to minimize your carbon footprint, right, you could do things like never own a car or, never fly on a plane. But there's some constraints there. It's like, well, maybe I don't want to do something so extreme. Is there a more reasonable measure that I could take that reduces my carbon footprint while I could still, live my life in a reasonable way? And so we would call those constraints. Okay, so what we're going to do is we're going to model a similar situation where we're going to optimize this box made out of a piece of paper. And so we're going to have some constraints on us, right? So the constraints that I'm imposing on this problem is the way that we're going to create our box. Okay, so you're going to end up taking this box and cutting corners, right? So you're going to take some corners out of the piece of paper, and we're going to fold up the box. Okay, so if you see on the screen right here, what you're going to do is you would measure out. Okay, so depending on what you want to do, you would measure out a square in the corner of your piece of paper. So I don't know if you can see something like this, right? I put some dotted lines there. And I want to cut out the same square on each corner, okay? Now, depending on how big those squares are, I'm going to get a different box, right? So if the squares are really, really small, when I fold it up, right, that's going to be a different box than if I cut really, really large squares. Okay, so somewhere in the middle, right, so somewhere in this process, I'm going to be able to get the box that has the largest volume. Okay, so we're going to try to optimize the volume of our box so we can hold the most stuff. Okay, so Nick, how big do you want your square to be that you're going to cut out of there? What do you think?
Well, I'm not sure. I just cut out squares.
Okay. So if we cut out squares, right? So if I cut out squares out of my corners, right? So I'll do this here for the camera. Go ahead and right. So I didn't measure these that well. But right. So if I cut out squares, what I'm going to get is I'm going to get a footprint that looks something like this, right? Right, so this would be the base of my box, and if I fold, right, if I fold it along this line that was created right here, right, so if I make this flat, you can see that this flap will then pop up, and this is one of the sides of my box, okay, so then I can go around and same thing, right, so if I wanted to, right, I could tape this corner right here, and that would be a side of my box. Here, and I can finally fold my last side. Okay. And so I just sort of did this, haphazardly, but I've now created a box. And so the question is, what's the volume? What is the volume of this box that I've created? Notice that there's no top, but that's okay, right? So I do have a box here, and the question is, what's the volume? Right, so if we look at this, we want to figure out, hey, what's the height of my box? What's the length? And what's the width? Okay, so Nick, are you able to measure your box there that you've created?
Yeah, I'll grab a ruler. All right.
Okay, so I'll put my while you give me the data, I'll record it on our board over here together. And so we've got this box that we've created, and what was so we need a length, we need a width, and we need a height.
All right, so length is about, let's see, a little less than 6 inches.
Okay, so let's just round it off. Let's call it 6 inches.
Yep. Width is about 3 1/3 inches. And then the height is about a little bit more than 2 1/2 inches.
Okay, so this was 2 1/2 inches. And your piece of paper was originally how big?
I'm not sure.
Was it just a standard sheet of paper?
I think so, yeah.
So it should be like 8.5 by 11.
11. Yeah, probably.
So this would be total 8.5 inches, and then and then along the top, right? So this should be 11 inches. Okay, so if I look at this diagram, right? So here's my box. What I want to do is I want to figure out, hey, with these measurements down here, where is the, like, can I draw on my diagram here where 6 inches would be, right? So which part of this is 6 inches?
So it would be, I think, the bottom before, with not counting the corners.
So the bottom, so like this would be 6 inches right here?
Yeah.
Okay, so using our highlighter, right? So this is 6 inches, right? Tool. So here's 6 inches right here. And then where would be 3.3 inches?
On the side, not counting the boxes.
Okay, so this 3.3 should be like here.
Yep.
Okay. 3.3, and then where's the 2.5?
It would be one of the dotted lines.
So one of the dotted lines, right? So this would be like this right here. So actually, all of these are going to be the same, right? Because they're squares. So all of these would be our 2.5.
Yeah, approximately.
Yeah. All right. So does this make sense? All right. So let's think about this. So the blue is 2.5. So if I took my 2.5 and then 6 and then another 2.5, do I get 11?
Yep.
And if I take 2.5 and 2.5 and 3.3, do I get 8.5?
Close enough.
Pretty close, right? So do you think we could modify one of these numbers to make it exact?
Probably the 3.3.
3.3 to what?
3.5.
Yeah, so that should be about 3.5, right? So, all right, so if we just sort of dial this in for some measurement error, it seems like our box is 2.5 by 3.5, right? So this will make this a 3.5 down here, and then by 6, right? All right, so our volume would be 6 times 3.5 times 2.5, right? So if we put that into Desmos, we get 6 times 3.5 times 2.5. That gives us 52.5, right? So our first attempt at this was 52.5 cubic inches. So my question is, can we do better than that, right? So can we do better than 52.5, right? So this is our first attempt. Could be the best, might not be. And so in a normal class setting, if we had sort of a bunch of people that were able to be here, we would gather a bunch of data, right? So I would have all the students do this. We would gather data, and then we would try to look at the result. But since we're just the two of us, Nick, what we're going to do is we're going to see if we can model this and maybe change some parameters around. So I'm gonna minimize this. This is our first example. We're going to keep it over there to use it as a guide, but then we're going to try to create a different example. So what was the defining characteristic? Like, what did you do to create your box?
You cut out the corners?
Yeah, so we had to cut out these corners. Now, you decided to make a 2.5 inch by 2.5 inch square, but did you have to do a 2.5 inch square?
No.
You could have done a 1 inch square, right? Or you could have done a 3 inch square or a 3.5 inch square. So I guess the question is, if I was thinking about this problem, this changes, right? So this quantity right here, however much I'm doing it, that's going to change. So can we maybe put a variable on that? Like, what letter would you want to call that if you put a variable on there?
Call it X, I guess.
You call it X, right? So this would be X. So that would be our height, right? So what you've just found there is going to be the height of this box is going to be X. And so I guess what we have to do is we also have to figure out what's the length and what's the width of this box. All right, so if that length is X, what I need to know is I need to know what this distance is here, and then I need to know what this distance is over here. And we said that, right, these were all X. Right, so just like we had in our other diagram. Right, so let's go back over here. So when I was figuring out the dimensions here, one of the checks that we did is we said, hey, does it make sense that this is 6? Because we did this plus this should be 11. We did this plus this should have been 8.5. Right?
Yeah.
So coming over to our new model, right, over here, we'll leave this other one on the screen. What do you think the green should be? Right, so we're gonna.
Green should be what's that here? 8.5 minus 2x.
Yeah, right. So 8.5 minus 2x, right? So the total over here is 8.5, and then I'm taking away these two right here, right? And so we know that these are going to be x. So I have the total 8.5, I'm going to take away the two x's, and that would give me 8.5 minus 2x, right? So that's what I'll call our width. And what's our length?
11 minus 2x.
Yeah, right, 11 minus 2x. Okay, so I put all this together, and now what we want we want to say, what's our volume?
So we just multiply them all together?
Right, so our volume is going to be, we're going to call it V of X, right, depending on what X is. We'd have, we'd have length times width times height, right? So length times width times height, which is just X, right? So if we think about it this way, if we just sort of color code everything, right? So our 11 minus 2x is in red, right? That's our length. Our width, right, was our green, right? So that's our 8.5 minus 2x here, and then our height is in blue, right? So we have our length times width times height. And so I guess the question we're going to ask is, what should I pick here, right? So what value of x should I pick that gives me the biggest volume? Okay. So before we sort of just go headline down this path, I guess I want to think about this for a second. And if I look at this, it's a polynomial, right? So I could graph it and look at the behavior of this thing. But it doesn't really make sense for me to think about every value of x, right? So like, I can't make x a negative number, right? So it wouldn't make sense for me to say x is -1, right? So I can't cut a square of length -1 out of this thing. So I think I only want to consider positive values for x. But is there a maximum value that I could pick, right? So certainly 0, if I just chose x to be 0, I just have a flat piece of paper, right? So that would be, my volume would be 0. But is there what's like sort of the tallest box that I could make?
Well, it's not going to be able to be greater than 9.5 or 11.
Right. So it certainly couldn't be more than 8.5. Right?
Oh yeah, it's an 8.
That's right. So that is an upper bound. I think we could say it's actually much smaller than that, though.
Because it's 2x.
Right, yeah. Right, so if I think about this green area right here, this can't be negative either, right? So 8.5 minus 2x, that can't be negative. Right, so if we're cutting down here, I have to make sure that there's still some space here in the middle, so I can't cut more than half. X can't be more than half of the piece of paper, right? So X has to be smaller than half this length.
Okay.
Right, so we're going to be considering X values that fall somewhere between 0 and 4.25, right? So we want to make some cut, right? We can't make a negative cut. So 0 would mean we don't cut it at all, and then we could have some length of cut there, all the way up to half the sheet of paper, right? So I could kind of cut all the way down half, and then maybe if we think about this for a second, maybe it doesn't even make sense for us to consider 0, right? So maybe we don't really want to consider 0 because that would just be a flat piece of paper, 0 volume. That wouldn't make sense. And then maybe we want to have some sort of width to our paper. So we don't want to cut all the way to half. We probably want to have at least a little bit left over there in the middle. Maybe we don't want to get all 4.25. Okay, so now this is our polynomial. And so let's jump over to Desmos and see sort of what we can see with this, right? So here was our previous volume, 52.5. So we had our volume function, which was this, right? So we have 11 minus 2x. And then we have 8.5 minus 2x, and x, okay? And what we want to do is we only want to look at this when we're somewhere between 0 and 4.25, Okay. So there's our equation, and then we can sort of zoom out here, right? So we see it's sort of really tall. So here's a nice Desmos trick for those of you playing along at home. So if you want to, you can put some values into a table, right? So we can do like 0.1 and then 2 and 3 and 4, right? So sort of a bunch of points in our range, and then Desmos gives you this nice little zoom fit feature that we can now get a quick window on our graph. Okay, and we don't need that table anymore. Right, so here's our graph. It goes from 0, right? And so you can see that it goes up, 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 and then the volume starts to come back down. So, so your original x was 2.5, right?
Yeah.
So here's where you were on your first guesstimate. You were over here you cut out a length of 2.5, and then you got a volume of 52.5. So my question is, was that the best that you could do?
No.
No. So how do I use this graph? Could you use this somehow to figure out what the largest box that you could make? What is it?
Well, if you look at the vertex, won't that be the max?
So this point way up here, right? The highest point up.
Mm-hmm.
Yeah, so even if I click on this, Desmos is nice, right? It gives me that, it sort of highlights that point of interest for me. Right, so this is 1.585, 66.148. So what's the interpretation? What do those numbers mean?
So 1.585 would be the length of the little squares we cut out, and 66.148 would be the volume of the box.
The volume, yeah, right. So the biggest volume that you could get is this 66.148. So out of a sheet of paper, using this method right here that we've decided on, right, the largest volume of the box that I could create is 66.148. Okay, and so that would be with a cut that is about 1.5, a little more than 1.5 inches. Okay. Now, if you were to give the dimensions of this box, right? So here's 1.585, right? So our height right here, right? If I make a note, our height was 1.585. And then what was our length and what was our width for this thing?
Length was 11 minus 2x.
Mm-hmm. So it would be 11 minus 2 times 1.585.
Yep.
And
then width was 8.5 minus 2x.
All right, so our width here is 8.5 minus, not divided by, minus 2 times this 1.585, right? So something like this. All right, so it seems like if I'm going to make the largest possible box out of these materials, I would have a length of about 7.83 inches, a width of 5.33 inches, and then a height of 1.585 inches, right? And so that's the best, that's the biggest, largest box that we could create. Now, one thing that I want to point out here is it seems like these numbers, like this could be an approximation. So we know that when we look at the Desmos graphing calculator, it rounds these numbers to 3 decimal places. So this could be rounded, right? So there could be more decimal places that go on here. And so if we wanted an exact answer, that's where calculus would come into play. Okay, so we would be able to sort of figure out where this point is using calculus. And so next semester, when you go off into calculus, you're going to see the techniques for figuring out analytically what are these maximum points, right? So you could get that ultimate precision using a little bit of calculus. Okay.
Yep.
All right, so now I'm going to kick it over to you. Does this make sense? Do we have any questions about it?
Yeah, that makes sense. Though I guess it might not be wise to like report our answer to so many decimal points places because we rounded in the first place.
So what do you mean? Where did we round in the first place?
When we were measuring the box.
Oh, right. Yeah. So initially, right. So when you initially measured, that gave you the estimates, but then we corrected for that, right? So remember,
Yeah,
we
okay.
changed your 3.3 to a 3.5.
Mm-hmm.
So then we did correct for that. But you're absolutely right. So if you're rounding initially, yeah, that might cause some errors later down. So that's a good tip for any time you're doing measurements. Rounding early and then doing computations on top of those rounds can lead to some significant errors, right? So you want to kind of avoid rounding as much as possible until as late as possible.
Mm-hmm.
Um, but as far as these sheets of paper, right? So if you measure them, I think they're pretty close, right? So the 8.5 by 11 sheets of paper are pretty close to the spot on measurement. So, um, but I would be pretty confident in this answer, right? So if I was going to instruct somebody how to build the largest volume box using this method, I'd be pretty confident in these numbers, right? So I would imagine that it's probably with the tools in a normal classroom or even in anybody's just normal household, it's probably reasonably difficult to measure out to a 1/100th of an inch, right?
Yeah.
1/100th of an inch. So that's probably pretty challenging. I mean, most people, I would guess that your standard ruler or tape measure is going to go out to like 1/8 of an inch. So these would be pretty challenging for you to get to.
Now, how would if we wanted the smallest possible value, would we just look at the bottom points of the graph?
That's right. Yeah. So you would kind of look at the minimums here, right? So provided that we do make a cut, right? So if we make no cut, we know that we have just a flat sheet of paper, and that is no volume, right? So it's 0. And then similarly, if we were over here, right, if we sort of had no side, our box would just kind of be a flat piece of paper folded over on itself. So those would have no volume. But assuming we don't do that, assuming we have some volume, is there a minimum to this?
Is it at the right, just barely above 0?
Yeah, so if we sort of zoom in here, just barely above 0. So I can't quite get to 4.25, right? But like, how close could I get, right? So you can see that Desmos is rounding here, right? So it goes to 4.249, and then it rounds up to 4.25. So these points are clearly on our graph. But if the closer and closer we get to 4.25, it's going to give us just smaller and smaller and smaller volumes, right? So it's never actually going to get to 0 volume. So this would actually, provided that you do want to make a cut and you don't want to cut the whole thing, this would have no minimum, right? There would be no absolute minimum to this graph.
Hmm.
That's right. So we could just keep getting smaller and smaller and smaller here, and our volumes would just keep getting smaller and smaller.
And we couldn't actually make that kind of cut.
Yeah, so it depends on the precision. So this calculator will only go out, it won't go all the way to that much precision. I guess towards 0, it is giving us some pretty good precision here. Right, so you can see that we can just keep making our cut smaller and smaller and smaller, right? So we could go down to, really, really, really small, right? So the closer and closer I get, right, I'm just getting really, really, really small volumes, but it's never gonna get to 0, right? So we can zoom way, way, way in. We're still getting smaller and smaller volumes. But we're never gonna get to 0, right? We'll never hit a minimum here. Just
Yeah.
keep zooming in, right? So here we're at, we have 0.00015 times, and then an 8, right? So when we're still really, 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 really small. Right? So this is all really small, and we're never getting We're never getting to 0. So this would have no minimum, but it does have a defined maximum. Okay.
But so if we wanted to get a smaller volume, though, we would you'd make either a really small cut or cut almost the whole way.
Correct. And that would give you pretty much just no volume, yeah. But like
Okay.
a flat piece of paper would have no volume. I mean, if you make just a tiny little cut off the end, you're going to be indistinguishable from a flat piece of paper, anyways.
Yeah.
But there's other questions that you could ask, and it doesn't have to be about volume. You could turn the question to maybe you want to minimize the surface area, right? That could be another question that you pursue here, where you start thinking about, hey, what's the area of the sides and the base? Right? How could I minimize or maximize my surface area? Right? So there's all sorts of different extensions that we could have to this. Okay. Yeah, I think this is a pretty nice problem. It's a classic one that you'll see this again in calculus, but we'll sort of change these values to what we call parameters, and then we'll use calculus to be precise with our answers.
Okay.
So we've got about 13 minutes left. I'm going to skip this, and let's see if we can jump over to rational functions. So this is going to be the last topic that we go over, and there's a couple of questions on web work. So I think there's just 10 questions. So through the last 10 minutes today, we'll introduce rational functions, and then so if you wanted to, Nick, you get a start on that stuff, or anybody watching at home. And then we'll spend time on Thursday going through rational functions, seeing what kind of questions people have. And then the following Tuesday is our last day of class. We'll see if we need that period, right? So if I don't want to try to cram too much stuff into the end of the semester. I know everybody's got a lot of stuff going on. So we'll see what we can cover on Thursday, and then the following Tuesday, if we have any additional questions and stuff, we can wrap everything up. But to give a quick primer here, we have this new type of function that we call a rational function. So the previous question was a polynomial. And a rational function occurs when you divide two polynomials, right? So we saw that, we could add polynomials, we can multiply them, we can subtract them, and we still get polynomials. But in this one case, if I take two polynomials and I divide them, I get something else, right? And so some of the examples that we see are going to be things like this, right? So we have like an x over x plus 1, right? These are polynomials, or this x squared minus 1 over 2x plus 5. And so let's go ahead and we'll come over to Desmos. Let's just bring up a new graph here. Let's just graph some of these things, right? So we got x over x plus 1. Right, so it looks something like that, and then right, 1 over x minus 1 give x over x plus 1. So like, what do you notice about these functions as I'm typing them in here, Nick? What are you observing?
There's like two different parts, and they mirror each.
So when you say two different parts, when I turn this off, you mean like there's this piece over here on the left and then this piece over here on the right? Yeah, so our function so it's not connected, right? It looks like there's this like gap here where it's broken up, yeah? Mm-hmm. So in calculus, we'll call this idea continuity, right? So if I were drawing this, I would have to pick up my pen and to keep going, right? So there's no way for me to draw it in one continuous line.
Now, why is that? Is that because you're dividing and you can't divide by 0, so certain quantities would make these undefined?
Yeah. So yeah, what would that quantity be when you divide by 0 here?
It would be -1.
Yeah,
So that's
right. So if I look at this function right here, if I were to plug in -1, I would get a division by 0. That's exactly right. Yeah. So that would give us this behavior where I'm going to have a point in there where we're undefined, right? So there's going to be this place where it goes away, and then we have this, right? So I'm dividing by 0 over here at 1. You can see that that's moved. And so would we divide by 0 on this one?
1 for that one, or for h of x.
Yeah.
Um, -5/2.
Yeah, -2.5, it seems like, right? So
Yeah.
right about here. And then, so we got our last one here. X cubed plus 2x minus 3. What did I call this? M of x. So it's x cubed plus 2x minus 3. We're going to divide all of this by x squared minus x to the 7th. Yeah. So what's sort of different about this one?
Um, They're not like facing each other. They're not like mirrors like the last one, the other ones. Or maybe they are, they're just bigger.
Yeah, it looks like there are mirrors around this, right? So there would be some symmetry to these graphs, yeah. So what were you saying about over here? You said if I look at the first one, when we picked out -1, that's when we divide by 0. And then over here, we picked out 1, that was when we divide by 0. And then this one, you said -2.5, that's when we divide by 0. It looks like that's where you have this break. So where do you divide by 0 on this one?
0.
Is there any other place that you might divide by 0?
1.
Yeah, so it looks like your behavior here when you talk about at 0, right? So you get this sort of break, but why doesn't that happen at 1? Right. So what's up with that?
I'm not sure.
And so if we look here, right? So if I get closer to 1, it seems like Desmos will tell me that it's undefined. So I am dividing by 0, but it seems like we have this distinct difference, right? There's something happening here where we have a vertical, we call this a vertical asymptote versus a hole in our graph, right? Versus a hole. So that's pretty, to me, that's interesting, right? So we might have to do some work trying to figure out, when does this happen where we have a hole, and when does this happen when we have a vertical asymptote, right? But yeah, so if we plugged in 0 and 1 into these things, and we noticed that, hey, if I plug in 1 into this function, I divide by 0, and then 1 and 0 here. And so I gave this prompt. We're going to be interested in finding some points. So we talked about these vertical asymptotes, these holes, but what else do you think you'd be interested in here?
Maybe like the vertex of the curve.
What do you mean by the vertex?
Sure, if there's not really one vertex.
Yeah, there's not. It's not like a parabola, right? So it's not like you have like a maximum value. So just sort of looking at these different graphs, it's like there might be things that we're interested in. So this one kind of looks funky. Like what do you think would be the points of interest on this graph?
Maybe the x or y intercepts.
Yeah, right. So x and y intercepts would be a good one. So what do we call the x-intercepts? Right, so like this would be our y-intercept right here.
Mm-hmm.
So the x-intercepts, what word did we use for polynomials? Started with the z.
Zeros.
Yeah, right, the zeros, right? So something like this, right, we'd be interested in figuring out, hey, what are the zeros? When does it cross the x-axis? So you can see that might happen at multiple points. We might be interested in figuring out, hey, what are these discontinuities, right? When are these vertical asymptotes there? And so we actually can get different asymptotes, right? So it looks like there's this line right here, right? So this is something that we call a slant asymptote. And then this right here, we can also have what we call horizontal asymptotes. And so our section 9.2 is all going to be about vertical and horizontal asymptotes. And sort of to start here, we're going to try to think about, hey, when do we get zeros of our function? So we've got about 3 minutes, but so if I look at these rational functions right here, what do you think about, do you think you could tell me some interesting points before we graph them? So let's take this r of x. What do you think is going to happen? What are some interesting inputs and what's going to happen at them?
Maybe 2 and 3, or negative 2 and 3.
What do you expect to be negative 2 and 3?
Zeros.
Mm-hmm. And what would be another interesting point?
Negative 1 would would give you an undefined.
Yeah, it'd be something, right? So let's go ahead and take a look. So x plus 2, x minus 3 over x plus 1, right? X plus 2, x minus 3. I'm going to take all this and divide by x plus 1. Seems like zeros, you said you'd expect zeros to happen at negative 2 and 3, which is good. And then x equals negative 1, it seems like we get this behavior where we do get this sort of vertical asymptote there. Right? And so what were you picking out, right? So how did you know that it was going to be negative 2 and 3?
Because that makes it equal to 0, or that part of the thing equal to 0.
Yeah, so we call this the numerator, right? So the top of the fraction is the numerator. So when the numerator is 0, that's going to be when we get zeros.
Yeah, I guess so.
And then you also said you should check when the denominator is 0, right?
And that'll give you the asymptote.
Maybe, yeah. I mean, that's certainly a good conjecture, right? But let's try something like this one here. So x cubed minus 4x, right? So let's try another one. So what are the zeros of that numerator?
0.
Mm-hmm. And
2 and negative 2.
2 and negative 2, yeah. So we would expect 0, 2, and negative 2 to come up, and it looks like 2 and negative 2 do, but why don't I'm not getting 0 as
well, because 0 would also make you divide by 0 as well.
Yeah, it looks like, so 0 is undefined, and then we get this sort of weird point down here that's a hole, right? So that's sort of interesting to me. So we're gonna have to reconcile this. So we'll talk about it more on Thursday. But yeah, we're gonna look where the numerator is 0. That's gonna be important. But we're also gonna have to check when the denominator is 0, right? And so we have these two competing ideas. We have polynomials. We know how to find their zeros. We'll look at the numerators. Where are those 0? We'll look at the denominators and figure out where those are 0. and then we're going to have to compare them, right? So it seems like if they match up, if they should share some zeros, then that's going to be a problem, right?
Yeah.
And so that leads us. We'll sort of put a cap on today with this zero quotient property that we sort of explored there, which was, if I'm gonna divide these things, I want the numerator to be 0, and I want the denominator to not be 0. Right? So I don't want to have this 0 divided by 0 situation. So this is a nice property, but we'll follow up with this on Thursday. But I think with this, you should be able to explore a lot of the homework. Okay, so on Thursday we'll try to finish up this stuff. We'll talk a little bit about vertical and horizontal asymptotes, and then if we can, we'll do some similar modeling problems like we did today with the box, except we'll try to optimize. We'll do a different box, and then we'll do a can, right? Like a soup can or something. How do we optimize those things? And so it turns out that when you set up your equations, you get rational functions and not polynomials. But all right, so Nick, any last questions before we sign off for the day?
Yeah, just quick. Are we skipping that polynomial division?
Yeah, so we're not gonna cover that. I mean, just with the time crunch, it's good to have in some situations, especially if I don't know where you're going to take calculus, but some instructors want you to do that by hand. So it's there if you want to review it, but I'm not gonna put it on our homework, and I won't put it on our final exam.
Okay.
Okay, and so are you planning to take calculus at Westfield in the fall?
I'm not thinking so, but maybe.
Okay, so if you do, the instructors at Westfield are not going to require you to know that.
Okay.
So when I built these materials, I want to prepare you for no matter where you go, right? So no matter what calculus class you end up in, you should be prepared for that instructor. But at Westfield, we tend to rely more. We'll allow you to use Desmos and do factoring and things that way. So.
All right.
Okay. All right. Well, thanks for stopping by today, and we'll see you on Thursday.
All right. Have a great day.
You too. See ya.
Bye.